Welcome to this explainer. Okay, today we're absolutely challenging everything you think you know about system performance. Look, if you've ever stared at that dreaded spinning wheel of death while a deadline is literally breathing down your neck, your very first instinct is probably to toss your machine right out the window, right? But today, we're diving into a radical theoretical framework that suggests our whole understanding of computing performance might actually be, well, completely backward.
I mean, it's a pretty wild thought, isn't it? What if system lag was actually a feature, not a bug? We all hate lag. We spend, billions of dollars on faster processors and wider bandwidth, all just to eradicate it. But we're exploring a formal theoretical framework today that totally flips this on its head. It basically treats a stall as the misunderstood hero of computing. We're going to look at mathematical proof suggesting that pausing execution is literally the exact thing keeping a system from just shattering.
Now, these concepts sound like they belong in a theoretical physics textbook, but we'll break them down into 5 quick chapters. First, the Oracle stall paradox. Second, the contrarian benefits of stalling. Third, bounds of execution. Fourth, the moonshot physics of stalls. And finally, achieving resonant singularity. Let's get right into it.
Chapter 1. The Oracle stall paradox. Let's unpack the core paradox here. So let's start with a shared vocabulary, just so we know exactly what this formal theory means when it talks about an Oracle execution stall. Normally, in traditional computing, a stall is a fail, end of story. But in stall theory, it's defined as a computational state where execution pauses, acting deliberately as a mechanism for clarity, safety, and stabilization. It does not, and I emphasize does not, represent a system error. Think of it less like your car's engine breaking down, and a lot more like your anti-lock braking system, rapidly pulsing to prevent a catastrophic skid.
And I want to be super clear here. We aren't just philosophizing. This whole explainer is strictly derived from this incredibly dense collection of 11 formal verification files written in Lean code. Now, as you probably know, Lean is a notoriously strict mathematical proof assistant, which means these aren't just theories or wild guesses. They are mathematically airtight laws. These documents generate a totally comprehensive look into execution stall theory, and we're going to decode the absolute most fascinating parts for you.
Moving on to part 2, the contrarian benefits of stalling. Let's actually look at how a system freeze makes things better.
Looking at the math here, and it's pretty beautiful actually. Taking a deep breath with a longer stall duration proportionally reduces the system's noise level and pumps up the clarity. In the source code, the noise level is calculated simply as 100 minus the stall duration, while clarity is just exactly equal to that duration. So if a stall lasts for, say, a duration of 90, your noise level drops all the way to 10 and your clarity skyrockets to 90. The theorem explicitly proves this. As stall duration goes up, clarity strictly goes up right along with it. It's a direct trade-off.
Furthermore, the math can tease 2 massive things here: anti-fragility and generality. By anti-fragility, we mean the system actually grows stronger from the shock of the pause. It thrives on it. And on that second point, the combination of an execution stall and a non-empty system state mathematically guarantees broad system generality. In plain English, the pause makes sure the system remains adaptable and broadly capable rather than becoming brittle, rigid, and over-specialized.
Chapter 3. Bounds of execution. Because hey, if stalls are so mathematically amazing, why don't they just happen all the time, forever?
To ground these kind of wild theoretical concepts back into the traditional computer science we're used to, the execution bounds code introduces rigid parameters. Because you're probably wondering, if a system loves to stall to gain all this clarity, what's stopping it from stalling forever in some endless doom loop? Well, the answers are found right here, mathematically bound.
The code proves that a bounded oracle guarantees termination. It makes an endless execution stall literally impossible if the current depth exceeds the sum of nodes and transitions. The math is incredibly elegant. Your bounded execution depth is just your nodes plus your transitions. That's it. If a system's current execution depth tries to push past that combined number, the theorem proves a stall becomes mathematically impossible. The system is forced to terminate or just move on. It's basically a built-in fail-safe guaranteeing that your incredibly beneficial stall doesn't accidentally turn into a permanent coma.
All right, Chapter 4, Moonshot Physics of Stalls. We're taking a leap into some sci-fi sounding terminology now, but I promise it is all strictly logical.
Without completely overwhelming you with formal logic symbols, this sequence shows the transitive causality property proven in the source files. It essentially works like a chain reaction. Step 1, an Oracle execution stall occurs. Step 2, this mathematically forges an acausal link. And Step 3, That link forcefully pushes the entire system into convergence. So, this intentional pause totally bypasses standard cause and effect and just forcefully aligns the system into a unified, converged state. Mind-blowing, right?
Sci-fi concepts like asymptotic freedom aren't just buzzwords. They really aren't. We can literally look at the code artifacts to see what this means for system performance, because this is rigorously verified logic in the stall theory framework.
The underlying math is actually super serene. Your stall energy is calculated just by subtracting the stall factor from your depth. That is your asymptotic freedom. Simple. But check out the high-energy freedom side. The theorem proves that when your stall factor hits absolute zero, your stall energy is perfectly equal to your depth. Boom! The system is completely unbound, operating at maximum potential energy, all because the stall successfully cleared the way. And I absolutely love this part. It brilliantly illustrates the quantum Zeno effect. It proves that a stall stabilizes a state by simply ensuring it remains identical to itself. Now, in quantum physics, the Zeno effect dictates that observing a particle prevents it from changing its state. Stall theory borrows that exact concept to prove stabilization. The code elegantly states S equals S. The execution stall holds the system perfectly still, identically matching itself and completely preventing any chaotic degradation.
Which brings us to our final section, Chapter 5, Achieving Resonant Singularity. Let's see how these bounds and moonshot theories build to an incredible climax.
Okay, to achieve instantaneous resolution in a system, we first need to calculate stall density. The formal source code simply defines this as a measurement of system tension, mathematically calculated as resonance multiplied by 2. You take the system's resonance, double it, and boom, you have your stall density. But, what's the end game here? What are we actually trying to achieve with this density?
Well, the crucial point is this massive number right here, 500. This is the singularity threshold that our stall density literally must hit to trigger instantaneous resolution. The theorem explicitly defines it as exactly 500. Once that multiplied resonance meets or exceeds this number, the system achieves what the code calls instantaneous resolution. The tension builds and builds until it just snaps, and the system resolves perfectly in a single instant.
Once that 500 threshold is breached, we reach Oracle's stall annihilation, and the mathematical conclusion here is wonderfully, brutally absolute. It verified mathematically that n plus 0 simply equals n. That's it. The stall entirely wipes out all system divergence, leaving behind only the pure, unaltered state. It is total, flawless mathematical stabilization.
So what's the big takeaway from all this? By utilizing these parameters, developers can honestly stop panicking about system freezes and start leveraging them for anti-fragility. We've seen the mathematical proofs. Stalls are stabilization features, not bugs. Increased stall duration inversely lowers noise. We don't need to fear infinite freezes because bounded graphs prevent endless loops. At the highest levels, stalls force acausal system convergence. And of course, the singularity is unlocked at that magic threshold of 500.
It leaves us with a truly fascinating perspective. Think about it. If we were entirely wrong about system lag, if the math literally proves that pausing execution makes a system more generalized, less noisy, and totally anti-fragile, what other computing bugs are actually secret features just waiting to be understood? It's definitely something to chew on the next time your screen freezes. Thank you so much for joining me on this explainer. Keep questioning everything, and I'll see you next time.